Hello everyone, I'm Bidong Kwang from KAIST, and my advisor is Myung-Soo Jung, who leads Computer Architecture in Memory System Laboratory. Today, I'll talk about our work, which is a hardware-software co-programmable framework for computational SSDs to accelerate deep learning service on large-scale graphs. Before we move on to the main talk, I'll give you a high-level summary of the talk. Graph neural network have shown great success in the various applications such as recommendation system, social network, and etc. The reason is that GNN can achieve higher accuracy compared to other machine learning models, and it can be well accelerated. However, current GNN works are only focusing on GNN algorithms, and we are missing out on GNN preprocessing. Thus, it's time to use HolyCGNN, which can accelerate both GNN preprocessing and GNN algorithm by leveraging the computational SSD concept. Then now, let's move on to the main talk. And firstly, let's go over how GNN works. GNN can achieve higher accuracy than conventional CNN model since CNN only can learn the distance information while GNN can learn the relationship between lots of data. For example, if a user queries the image which has a characteristic of pain, then CNN responds woman near the sofa, while GNN can respond the pain. Then how can GNN algorithm learn the relationship? GNN requires two input data such as graph structure and node embedding. And node embedding includes lots of features of each vertex in graph structure. And GNN can learn the relationship by aggregating the neighbor's node embedding and transform the aggregated node embedding to abstracted information with MLP model. By the way, what do we have to do before GNN algorithm execution? First, we have to prepare neighbor-oriented graph structure for embedding aggregation. Second, we also need small input data, which can be routed into the accelerator memory. Thus, GNN preprocessing firstly perform the graph preprocessing to prepare neighbor-oriented graph structure. Graph structure is stored as update-friendly edge array. Then graph processing converts the edge array to neighbor-oriented adjacency list. And after that, GNN preprocessing performs the batch preprocessing to prepare the small graph. And the insights comes from that the node sampling can significantly reduce the amount of data to process the GNN without an accuracy loss. Does this sample both graph structure and embedding? By the way, why is GNN preprocessing matter? Let me explain the problem of GNN preprocessing and I'll clarify the design consideration. Here, I visualize you the end-to-end GNN inference process. GNN preprocessing is performed on host CPU and it sends the small input data to accelerator. And we analyze the end-to-end GNN inference execution time and sorting the graph data set with the graph size. And let's break down the execution time into graph preprocessing, embedding I/O, batch processing, and pure inference time. As shown in the graph, graph preprocessing and embedding I/O is dominant contributor of execution time, not the pure GNN inference time. Also, please note that we cannot perform the GNN, which cannot be routed into the host memory due to the out-of-memory issue. Then what do we need to do for the new GNN acceleration system? First, we suggest to store the graph directly as a neighbor-oriented format, but also update efficient. Second, we also suggest to process end-to-end GNN inference near storage. Based on our design considerations, we propose a new GNN acceleration framework called HolyCGNN. HolyCGNN basically adopts a concept of computational SSD. And unlike the conventional in-storage processing, CSSD decouples the compute unit from the storage resources. So we rely on our HolyCGNN framework on the FPGA. Also, we separated FPGA into share region and user region, and share region is for essential hardware logics of HolyCGNN framework, while user region is for GNN inference acceleration, which can be customized by users. So, when users send their bit file, the accelerator builder engine in our HolyCGNN hardware program the hardware logic on the user region. And HolyCGNN also provides three types of GNN algorithm accelerators for the user who are not familiar with the hardware programming. And also core in the share region that executes GraphStore and GraphRunner. GraphStore converts array to adjacency list and store both adjacency list and embedding to SSD. And GraphRunner processes GNN processing and GNN algorithm near storage, and it can access the graph data via GraphStore APIs. Then now you understand why HolyCGNN is required and how it works. Then from now on, I'll explain more details of GraphStore and GraphRunner. The main goal of GraphStore is to convert the graph semantic to SSD semantic, which is logical block addresses, and it separates the SSD space into embedding space and neighbor space for making sure update efficient. And in the embedding space, embedding table is stored, and if there are new vertices, it grows up. While enable space stores enable list for vertex, and it grows down. By the way, why are there two types of neighbor list? We get the insight from the Paulo distribution of the number of neighbors, which is the nature characteristic of graph. So in the graph, there are lots of low degree and few high degree vertices, and we separate them as different types based on the page size. And GraphStore also manages the different vertices types with the different mapping table. And high degree type logical page only stores single neighbor list, while low degree type logical page stores many neighbor lists. And for the high degree type, if new neighbor is added, then GraphStore allocates one more LPN to vertex and updates the high degree type mapping table. And for the low degree type, as there are multiple neighbor lists in a single LPN, low degree type mapping table only records the lowest vertex ID of co-located vertices. And now I'll explain about the GraphRunner. And GraphRunner is programmable inference model, and it converts program semantic to execution semantic. Programmer programs a GNN inference sequence as a data flow graph, while GraphRunner executes the data flow graph by converting the operation to counter. By the way, why are there gap between the program semantic and execution semantic? Because there are many devices in the HolyCGNN hardware which can process the same operation. For example, vector addition can be executed on a CPU or accelerator. Note that users can add their own customized accelerator and also their accelerator's hardware code. At last, let me introduce the evaluation result of HolyCGNN. For the evaluation, we implement HolyCGNN prototype with the 14 nanometer FPGA and SSD. And we test 13 graph dataset, and we categorize them into small and large based on the number of edges. And we compare the HolyCGNN performance to high performance GPUs, and as shown graph, we achieve 2 times faster inference time for the small graph, while can achieve more than 100 faster inference time for the large graph. Also, we test energy consumption, and we achieve 33 and 16 better energy consumption for each GPUs, and almost 500 better energy consumption for large graph. And this energy efficient execution is due to the low power computing of FPGA. Then from now on, I'll show you our demo which learned the graph neural network on our HolyCGNN prototype. We build both essential hardware logics on share region and heterogeneous GNN algorithm accelerator on user region in FPGA. After the HolyCGNN preparation, we initialize GraphStore. First, GraphStore reads HRA file. Second, it converts HRA to the agency list. Third, GraphStore reads the embedding file and writes to SSD. At last, it writes the converted agency list to SSD. As shown in the demo, we took 32 seconds to initialize the GraphStore. And during this time, HolyCGNN also generates the mapping information for both adjacency list and embedding. Then now, let's compare the GNN inference performance of HolyCGNN and high-performance GPU. HolyCGNN is on the left and high-performance GPU is on the right. I break down GNN inference time in HolyCGNN as read GraphStore, which loads the mapping table of both high degree type and low degree type from the SSD, and GNN preprocessing, which is performed in CSSD, and the GNN algorithm, which is pure inference time. Also note that during the GNN preprocessing in HolyCGNN, only batch preprocessing is performed because the graph preprocessing is already performed when we initialize the GraphStore. In contrast to HolyCGNN, we break down the GNN inference in high-performance GPU as reading HRA and embedding from SSD, performing both graph and batch preprocessing, and processing the GNN algorithm. Our HolyCGNN can achieve 361 milliseconds of end-to-end GNN inference, while the high-performance GPU takes almost 35 seconds to process the end-to-end GNN inference. It means the proposed HolyCGNN is almost 100 times faster than a high-performance GPU. Before I end this presentation, let me conclude our work. We implemented hardware-software co-programmable framework for computational SSDs, which can accelerate deep learning service on large-scale graphs. And our main contributions are, first, we propose the holistic solution for both GNN algorithm and GNN preprocessing. Second, we implemented fast and energy-efficient near-storage GNN inference infrastructure. Third, we support easy-to-use and user-customizable interfaces. Thank you very much for your attention. And if you have any questions, then please freely ask to me.